Okay, I haven't mentioned the solvent, and I think the solvent tends to, it drove me crazy when I was, so water here is the solvent, and there's nothing necessarily that points out, there's nothing to tell you that water is the solvent, all right? This is sort of, you have to know this from doing chemistry. Water can be a reagent. You've all seen reactions with water. So the solvent, what the solvent does, so SN2 and E2, this is a kind of another level down in terms of sophistication about the reaction. Pretty much every chemical reaction you ever do will be done in a solvent. Right? That's why we're mostly water. You've all heard that, no doubt, right? That a human is mostly water. The reason is we're driven. Okay, so if you think about what makes up an animal, you've got water. You've got all this water. You've got a skeleton of some sort, exoskeleton. We have an internal skeleton, which is mostly inorganic. And I'm not a biologist, certainly not a physician, but you know the bones basically are there. They definitely are not inert. They break, they get diseased, they can be strong. I mean, the skeleton is amazing, so it's not inert, but it's also not doing a ton. The rate of chemistry in the bones is a lot lower than the organic bits. And then you've got all the organic bits. These are the reactions that let us, eat a piece of bread and turn it into energy to walk around and talk. All of those are organic reactions that are taking place in solution. Right? So the solvent is water. That's why we're mostly made up of water. If we didn't need solvents to sort of support reactions, we would all weigh a lot less. Okay, so there's almost always going to be a solvent indicated in the reaction. And that's just what everything is dissolved in. You guys have been doing some chemistry now. You've got this sort of, you need a medium for it. The solvent is there. There's always more molecules of solvent than anything else. And so if the solvent can react with any of the reagents, it will. Right? Like we're doing chapter 7 right now, so I'm focused in on the nucleophile and the leaving group. Right? But if I mix chemicals together, they don't know that we're talking about chapter 7. They just do what the universe dictates they do. So, you do have to consider the solvent. Will the solvent react? When you look at a reaction scheme like this, right? You got a reagent, you got a solvent, you got a temperature. You have to take all of that into account. So if the solvent will do something, you should have it do something. But the solvent can also play a more subtle role, even if it doesn't necessarily react. Right? If the solvent stabilizes the reagent, the reaction is going to slow down. Right? For a reaction to happen, you want these molecules to do something. If the solvent stabilizes the reagents, either reagent, the reaction gets slower. If the solvent destabilizes the reagent, the reaction gets faster. Make sense? Okay. So I'm going to erase some of this stuff over here. So we've got an SN2 reaction. In this case, we have an SN2 reaction. This reaction is really driven by the nucleophile, right? So the reaction is driven by the sulfur anion. Same way in an E2 reaction, that's going to be driven by the strong base, the thing that goes in and grabs the hydrogen. Okay, so this is driven by the sulfur anion. So if we stabilize that sulfur anion, the reaction gets slower. If we destabilize it, the reaction gets faster. So in this case, the solvent is water. Right, so we've got all these hydrogen bonds in there. The water has a hydrogen bonded network. But the other thing, the sulfur anion, and sodium salts tend to be really soluble in water because that anion can interact with the water. Remember, back to solubility, the more a substance can sort of fit into the interconnectedness of the solvent, right? In water, the dominant intermolecular force is hydrogen bonding. So anything that can hydrogen bond is going to be really soluble. And the more it can do that, that doesn't just stabilize the water, it stabilizes the anion. All right, so a protic solvent, and so I should probably define that. Really, protic solvents are going to have OHs and NHs in them. Those are hydrogen bond donors. Right? So, so anions are stabilized by hydrogen bonding to the H in water. So what I've just told you is water should stabilize the anion, and the anion we want to drive the reaction, and yet the reaction happens. So like I said, the solvent is a fairly subtle effect. All right? This solvent, you can't look at the solvent and say anything about which mechanism will be favored. The solvent will not tell you SN1 or SN2 or SN1 or E1. The solvent is going to tell you how fast the reaction would be relative to other conditions. So, for example, not a space, protic. There are going to be three let me draw, sorry. There are three polar aprotic. So you do need the solvent to be polar. Right? So if you want to stabilize the anion, well actually that's not even true. Let me back up and tell you what I skipped a couple of thoughts. Right? So water stabilizes this anion. To make the reaction go faster, we would like to destabilize that anion relative to water. So we need to get rid of this hydrogen bond. Okay. So we need a solvent that doesn't hydrogen bond. Make sense? All right. So you want a solvent that doesn't hydrogen bond. Well, like hexane. So hexane doesn't. You guys at home know what hexane looks like. All right. Here's hexane. You guys here know what hexane looks like too. I don't know what to do with myself if I'm not drawing molecules. So hexane doesn't hydrogen bond. So maybe that would be a good solvent for this reaction. There's two problems with that. All right, so hexane's not a good solvent for this reaction. The first and biggest, most important reason is sodium thiomethoxide is a salt. It's really polar. It's not going to dissolve in hexane. Hexane's a non-polar solvent. All right, so the hexane just won't dissolve your reagent. So again, the solvent has to support all the reagents. You have to get a medium where all the different reagents can come together. And so if you have a case like this where you've got, right, this organic molecule is actually pretty non-polar. This molecule would dissolve in hexane really nicely. Sodium thiomethoxide actually dissolves in water. All right? So sodium thiomethoxide won't dissolve in hexane. The organic compound, I'm going to come back to this in a minute, doesn't dissolve in water all that well. Okay, so hexane is going to be a poor choice because it doesn't dissolve into the two reagents. It also it's non-polar. And if you think about the transition state has charge kind of distributed all over it. Right? You've got a partial CS bond, a partial CBr bond. So electrons that's a very polar transition state. So remember, kinetics. If we want to make a reaction faster, we want to destabilize the reagents, stabilize the transition state. Hexane's going to destabilize the transition state. So hexane's neither going to dissolve everything, nor is it going to help the transition state or the rate. So you need a polar solvent, something that will support polarized molecules. But you need it not to hydrogen bond. And so there's dozens of these, okay? I'm going to ask you to learn 3. One, you should already know a little bit, acetone. It's a ketone, so own ketone. You just got 2 methyls on a carbonyl. And then these, and I'm not going to ask you to draw those structures, right? You should know that they're polar aprotic solvents. I would like to minimize how much memorization of just stuff you have to do. Like if you needed to go do this reaction in the lab, you'd look up literature references. They would say to do DMF. You would look up what DMF is. You'd work with it. But I just want you to notice they're very polar, right? So you've got a carbonyl. They're all going to have like carbonyl type things with a significant O minus something else positive resonance structure. And they don't have any H's on the O's or N's or S's. So they can't hydrogen bond. All right, so if I ask you how to improve this reaction, you've got 2 ways of doing that. One, the solvent, like I said, water doesn't dissolve the starting material, the organic starting material all that well. So in lab, you've been doing extractions and stuff. If we asked you to, you need to do an extraction with this compound, this bromide, it's going to be in the organic layer. So you could change, ways to improve this reaction might be to change the water to ethanol. Right? Ethanol is more organic, you've got that ethyl group there. The bromide is going to be more soluble in ethanol than it would be in water. But even better, don't do this in ethanol, do this reaction in acetone. Right? So now again, acetone's an organic solvent. So it's going to dissolve the alkyl halide. It's polar. It can dissolve the sodium thiomethoxide. And it's aprotic, so it's not going to hydrogen bond. It's going to dissolve the sodium salt mostly through coordination of that sodium, right? The carbonyl, the partial negative on the oxygen can coordinate with the sodium plus. Right? So this would be, the upshot is acetone would be a better solvent for this reaction than water or ethanol or hexane. And I think having gone through all this, I think I know why students are always looking at the solvent. It's a more sophisticated, nuanced piece of the reaction. And so I wind up spending a lot of time talking about it. And very logically, you might think the stuff I spend a lot of time talking about is more important. Everything I did, solvent should be the last thing you look at. You should start over here. Is there a leaving group? Is there a good nucleophile or a strong base? Are there beta hydrogens? You should figure that out, and that's going to take you one way or the other, right? So if there's no leaving group, you're not in chapter 7, which means on exam 2, if you look at a reaction, there's no leaving group, you would say nothing is going to happen here. There's not going to be a reaction. There's no way for you to know. It may be a chapter 12 reaction, right? But if you haven't had that yet, so you're fair to say nothing will happen. But odds are I'm going to put a leaving group in, right? It's not a real good test if I don't. So is there a good nucleophile or a strong base? The answer is yes. That strong nucleophile or good base is going to drive the chemistry. You're going to do SN2 or E2. If the answer is no, there's not a good nucleophile or a strong base. So if you've almost got to have a weak nucleophile or a weak base. So like here, if we didn't have that, right now we got water. And water is a weak base and a weak nucleophile. So we can get a reaction, a nucleophilic or an elimination reaction. It just can't be SN2 or E2. So that means it's going to be E1 or SN. All right, if you don't have any nucleophile or base, right? If there's just not weak, strong, whatever, there's just nothing there, then you don't get any reaction. Again, you don't get a reaction. But the next important question is, are there beta hydrogens? So if there are, you can do elimination. If there aren't, you can't do elimination, right? No beta hydrogen, no elimination. And then you should come to these questions in the middle. Is the nucleophile a strong base? If it's not, right, if you've got a good nucleophile that's not a strong base, SN2 is very likely. But you got to check that, because you come down here, like if the carbon has a leaving group on a tertiary carbon, you can't. They interplay a little bit, but you really need to go in order. That's why that's why I put a flow chart up, right? Flow charts give you that. A lot of students like to start with the temperature and the solvent, because those are right there. Like, you don't have to do a lot of thinking. The reaction is going to say, it's going to have something you might recognize as a solvent. Temperature is easy to, like, temperature you've been talking about since you could talk, probably, right? It wasn't your first word, but it was probably in the first 200. Maybe not temperature, but hot, cold. So, it's an easy thing to hang your hat on. It's just the wrong thing to hang your hat on. The temperature will tell you if elimination or substitution, if it's a really high temperature, elimination's favored. Really low temperature, substitution is. Again, if it can happen. And then the solvent really is subtle. All right, so you would absolutely, in the reaction I first put up, it would absolutely be an SN2, even though it's in a protic solvent. It would still be, you got a really good nucleophile, you got a primary alkyl bromide, that's going to be an SN2. It'll be in water, so it won't, it'll be a slow SN2. And you could speed it up by putting it in a polar aprotic solvent. But don't let the solvent trick you into going down a path before you should. Yeah.
Will they ever kind of contradict each other? Like, what if there's really high temperature but there's no beta carbons?
Yeah, absolutely. So that's what I mean. It's a flow chart. So these questions come first.
Okay.
Let me show you an example of that. I'm going to erase some stuff here. I'd actually meant to do another reaction, but it was kind of equally complex. So, like you say, okay, so that's not a T, that's a T-butyl there. It's not cot. Right, you got a leaving group, chloride's a leaving group. And now, if you skip ahead, if you're like, okay, it's 120 degrees, man, that's going to be an elimination. I've got a really strong, bulky base, that's going to be an elimination. Right? Everything is sort of screaming, this is going to be an elimination reaction. But alpha carbon's got the chloride, beta carbon's the carbon bonded to it, and there are no beta hydrogens. There are no hydrogens on that carbon. Okay, so the product here, if anything happens, it is going to be a slow, that would be the product. It'll be a slower SN2 than if that O was like a hydroxide, right? The T-butyl is bulky, and again, for the SN2, the nucleophilic atom and the electrophilic carbon have to come together and make a bond. Okay, so if that nucleophilic atom is dragging a whole bunch of stuff with it, it's going to make a bond to that carbon slower than it would otherwise. But this reaction cannot do elimination because there's no beta hydrogens. So like I said, it's really important to go in order. Especially with those three questions on the right there under chapter 7. You've got to ask those first. You don't actually have to ask them in that order. I guess, just as long as you know what the answer means. So you could ask, is there a leaving group third? But if the answer is no leaving group, then you're done. So it makes sense to ask that one first. The next two are sort of interchangeable. So yeah, like I said, and this would be an SN2 even though it's in a protic solvent. All right, any other questions? Yeah.
So is the type of the carbon it's on, isn't that more important than the top one on the ion?
Yeah, they're in groups.
Okay.
Yeah, so you don't have to necessarily ask them in exact order. The type of the carbon is on can be really important. So if it's a tertiary carbon, no SN2. If it's a primary, it's probably not going to be SN1 or E1 real well because the primary cation's poor. And if it's a secondary carbon, the leaving groups on secondary carbons they can do kind of all four of the mechanisms, right? And they can rearrange them. The cation you get if you're doing E1 or SN1 is a secondary cation. It's not that stable, so you can see cation rearrangements. And the other thing to keep in mind with the secondary carbon, if it's chiral, and it probably is, you've got to pay attention to the stereochemistry. Like here, you didn't really have to pay attention to the stereochemistry because the leaving group's on an A chiral carbon. Just draw you could draw like I've drawn it. You could draw the S methyl up there. You could rotate things right. It doesn't really matter. Yep.
On the test, when we're asked a question like this, will it be possible that it'll be doing more than one mechanism?
Yeah, it is. That's and especially like if I don't put the temperature down, like not putting a like here, I probably wouldn't put a temperature down because you can't do eliminations. There's no E versus S thought. So it's either that, or if I don't put a temperature down, I really kind of mean it's going to be like. And I think I did one like that on. Seems like I did one like that on Friday, where it was sort of like all these different products could come in. So you can either draw all of them, or on a test, if you draw one, like if you really can't tell what the major product is, then if you give me the major elimination product, I'll be like, okay, the elimination would happen. If you give me the major substitution, I'll think substitution. Okay, so I will let them hear. So this really what I was trying to do. This is the thought process as you go through these reactions. So you need to get into Wiley Plus and book problems and work through these. There'll be a quiz toward the end of the week that basically you'll have to work over the weekend to sort of try to test how well you can get through that. And I would also kind of pay attention to every class. This is basically the class this week. I'm going to put a problem on the board. Class will work it and we'll talk it through. So you may not need to get the discussion so much because you've sat through the discussion here, but it's probably worth looking at the problem and seeing if you can predict the answer. All right, so let me come by and